It's a very great pleasure to introduce our speaker for tonight, Dr. Mike Corcoran from the Catholic University of America.
Can you talk a little louder, please?
He got his PhD from the University of Pennsylvania in 1988, and beginning with his PhD research, he focused on the remarkable behavior of very massive stars, both massive stars in isolation and in binaries. And the special thing about massive stars, they are really very different from stars like our sun. They follow the precept, burn brightly and live briefly, and have many explosions along the way. Among other things, they're the ones who produce a major class of supernovae, and that produces a lot of the elements that other stars and planets form and people form out of. In particular, Mike has performed a lot of research on Eta Carinae, which is the most massive star within 10,000 light years of us. Ever since his PhD, he's carried out his research, much of his research at NASA Goddard, and until recently he was associated both with the University of Maryland doing research at Goddard. Now he's a senior research scientist at Catholic University doing research at Goddard. In addition to his research and teaching, Mike works at NASA's High Energy Astrophysics Science Archive Research Center, which you might know through the acronym HESARC. Some people come across very frequently, where he's archive scientist for several high-energy missions. And at that center, he writes the High Energy Astrophysics Picture of the Week, which highlights new developments in X-ray and gamma ray astrophysics. Those are usually very instructive, a nice way to keep up with what's going on. Mike has also very recently taken up a very prominent but demanding position as Secretary of the High Energy Astrophysics Division, High Energy Physics Division of the American Astronomical Society. And recently that meant that he had to not only handle the complicated logistics of a meeting they had out there at Sun Valley, Idaho in August, but also take care of a large number of attendees at that meeting who stayed to witness the solar eclipse. That was probably quite tense. Dr. Corcoran.
Thank you, John. Okay, hopefully everyone can see that. I never know what color scheme to use for slides. Every projector is a little different. But anyway, thanks. I'm really happy to be here. This is my second time speaking to the NCA in this room. I think it was here about 15 years ago, so I'm really happy to be back. So as John said, I'm going to talk about tonight's topic, the lives and sudden deaths of extremely massive stars. So we're not even just going to talk about massive stars, but I'm sort of going to talk about the objects that are on the extreme tail of the stellar mass distribution. So there are a number of issues and questions. This is a sort of a topical summary. First of all, to understand what extremely massive stars are, we of course have to understand what is a star. And most of the talk is going to be discussing how big and massive a star can be. Observationally, how do we determine that? What are some of the both observational uncertainties and theoretical uncertainties? I'll talk about a few case studies, some of the more extreme examples of these objects. Then briefly run through how massive stars evolve, almost as rapidly as they actually evolve. Talk about massive stars through the cosmic ages, and then leave it with some conclusions, and hopefully point you to some upcoming events that are going to be very, very exciting. I want to encourage questions during the talk, so it's it can be very interactive. I'll hopefully leave time for questions at the end as well. So to get things rolling, I want to have a question for the audience. So what is a star? And if you know the answer, please don't answer. Let people who don't really know the answer. So does anybody, give me a definition of what a star is?
A massive ball of burning gas.
Massive ball of burning gas, okay, that's pretty good.
Thermal, using, well, it fuses atoms together to make energy.
Right. So let me maybe make this question more specific. So what's the difference between a star like the sun and the Earth? There's some obvious differences, sizes and temperatures and so forth, but what's the fundamental difference? Yeah.
Thermonuclear reactions.
Thermonuclear reactions, right. A star is only a star because it produces energy in its core. It's got a thermonuclear furnace burning at the very heart of this ball of gas. So I just saw these somewhat definitions. Fundamentally, a star is a fixed point of light in the sky. We know they're not really fixed; they move around actually, and they explode and disappear sometimes. But to the ancients, it was known as just a fixed point of light against which a background against which the planets move. But physically, it's really a hot collection of ionized plasma. Ionized means it's gas, which is electrically charged, and it's held together by self-gravity, which is actually opposed by internal pressure. It's not actually only opposed, but these two forces balance each other. The gravitational force pulling the star inwards is balanced exactly by the internal pressure that the star generates. So a star is a very stable object as long as it can generate this pressure. The pressure is due to both the thermal motion, or just the fact that the atoms in this plasma are at very high temperatures. They move around very, very rapidly, generating pressure. It can also be due to internal radiation which the star generates. And we'll see for these extremely massive stars, internal radiation is actually a very, very important component. It's actually the dominant component. As a result of all this, stars are photon factories. They give light to the universe. They're chemical factories. They give chemicals to the universe. John mentioned how they produce all the chemicals needed for life and planets. And they are also possibly thermonuclear time bombs. They can be very dangerous objects to get too close to. So the main question I want everyone to sort of think about is how massive can a star be? We actually know fairly well what the lower limit of a stellar mass is. It's about 0.1% of the stars of the sun's mass, and we know that because at that mass, the star is too cool and not dense enough at its center to generate thermonuclear reactions. But what about the other end of that limit? What do we know about the sort of the upper limit to how massive a star can be? So to understand this, we need to understand something about how stars form. So this is a very, very brief overview of star formation. So stars form out of clouds of gas and dust that exist in galaxies and maybe even outside of galaxies. This gas is at a non-uniform density. You could have an interaction which might push part of this cloud, cause a little piece of it to become more dense in its surroundings. And what happens, that generates a runaway gravitational attraction. So if the overdense region will have a slightly higher gravity than the surrounding region, so mass will fall into this overdensity region. Of course, that makes the region even more overdense, increasing gravitational attraction, and so material starts to funnel down onto this region from all over. And the region grows in mass and gravity. Compression, though, as this material is being gravitationally compressed, the compression causes it to heat up, and that generates a pressure on the inside of this collapsing cloud, which wants the cloud to expand. So you have these two forces that are opposed to each other. And also you have to throw in rotation, because things, even if they're spinning almost negligibly as they collapse, the rotation gets enhanced. And so material mostly accretes not all over the star, but in a disk. And so a star only forms if the gravitational pull inwards of the accreting material is larger than these forces that are outwards, the pressure force and also the centripetal acceleration of the material as it's rotating. So here's a brief video of how stars form. I guess hopefully this will play. This is from the Science Channel. It's a nice program that Kim Weaver, often has very fairly accurate depictions of science. This is a depiction of how stars form. We think material mostly spirals into the central star, which is here in a disk like this. This disk can also form planets if its conditions are right. And you saw that jet. Material, as it falls into the star, forms a jet. And at some point, this object that's accreting material becomes a star. And the point is exactly when the thermonuclear fires at the very core of the star, turn on. Hydrogen starts to fuse to helium. The star starts to generate energy by turning mass into energy, and you have a star. As a star forms, it can then blow away the rest of the disk, or the disk can remain in the form of planets. So the star turns on, thermonuclear reactions begin in the core. First, for an object like the sun, when the core is at a temperature of 15 million degrees. So that's an extremely high temperature. The density here is about the same density as that of lead. And once those thermonuclear fires turn on, the star then becomes stable and has a source of pressure outwards that supports it from collapsing further. So here in this beautiful picture, this is in the Carina Nebula. We'll talk about this region again because it's a very interesting region of star formation, especially massive star formation. But you can see a cloud here that exists in the Carina Nebula. It's getting bathed by ultraviolet radiation and evaporated from stars that are over here. You can see gas streaming off. You see these beautiful streams over here. If you look very closely right here, I'm going to go close to it. Right here you can see a jet of material that's being shot out from an accreting star. A star that you can't see that's buried within this thick cloud of gas and dust. So even though the stars are forming, it can be very, very difficult to actually look at this process in detail. We do have some ways to penetrate these clouds using X-ray emission that the forming star generates, and also looking at infrared radiation, which can penetrate through the cloud. This is once the star is formed, you can see the thermonuclear core at the very center. There's a outer-lying envelope which contains most of the mass of the star, through which the energy generated in the core radiates. And then for a star like the sun, you have this quote-unquote the surface, the photosphere. Of course, it's not a solid surface, but it's a region where most of the light is generated. It's actually a very thin region at the outer edge of the envelope. And for the sun, you see we have these prominences and all sorts of activity that happen above the surface. And we also have the corona. You hopefully you've all seen the corona. This is a image of the corona taken during the during the eclipse back in August. So you see this material streaming out. The material in the corona then can move away from the sun entirely, forming the solar wind. The solar wind is rather weak, although it does have very strong, very dramatic effects sometimes. A couple of days ago there was an X9 flare from a sunspot that shot out strong coronal mass ejection. Yep.
A couple of questions back here. I don't think you can see through the
No, I
lights.
can't actually. So
Yeah,
give me a good wave.
I've had my head up for several while.
Oh, sorry.
There are several of these disk and jet situations at different scales.
Yes, that's right.
I don't want to get you off there that really. But I would suggest that these jets have a helical property that's not been investigated a great deal or isn't much discussed.
Some jets you can actually see the helical structure.
Yeah.
Some jets associated with active galactic nuclei, for example, are thought to be bounded by the magnetic field off the disk.
Right.
And this magnetic field generally has a somewhat helical helical
There
structures.
should be a magnetohydrodynamics accounting for the magnetic field, the angular momentum, that produces this sort of thing.
Yes, and people have been modeling this. It's a very complicated physical problem, as you can imagine, because you're dealing with so many competing forces: gravity, magnetism, electricity, the population of the exact population of charged particles you have, the way
And
it
it has a
rotates.
fairly generic solution.
But yes, it's a very, you're exactly right. It's a very common phenomena that we see in astrophysics on all spatial scales.
Thank you.
So is there another question? Okay, so that's, yeah, in a nutshell, that's how stars form. And, a lot of that knowledge has actually been obtained over the last couple of decades, both theoretically and observationally through, beautiful observations like we see here in the Carina Nebula of stars actually forming these disks and these jets. So overall, the idea of how, the understanding of how stars form is okay. It's fairly solid. But there is a problem of mass. That we understand how stars like the sun can form, but as stars get more and more massive, if you try to grow a star, you try to form a star with a very, very large mass, you find that there's actually a problem. The problem is that as you increase the mass of the collapsing clouds, so you're trying to accrete more and more material, the gravity increases, which is good, that helps pull the star together, but the internal pressure, and this is mostly due to radiation, increases even more. And that's bad because that sort of makes very, very massive stars hard to form. And you can think about equating these two, taking the internal radiation pressure and setting it equal to the gravitational pressure inwards, and that can give you a limit to how big the star can be. Arthur Eddington in the early 1900s thought about this exact problem and defined a quantity which is now called the Eddington Limit. He didn't call it the Eddington Limit, but we call it the Eddington Limit now in his honor. And this is when the outward pressure of radiation from a star, or a accreting protostar, a star that hasn't turned on yet, balances the gravitational attraction inward. So the existence of this Eddington Limit, in theory, produces a upper limit to how massive a star can be. The Eddington Limit is also a concept that has a large application in astrophysics as well, and but I won't really get into that right now.
One thing,
Yeah.
before we go back there, it said, okay, right above Eddington Limit, it says, will not allow the cloud to contract enough to form a star. Wouldn't it be the case that would prevent it from growing any larger, but still give you a smaller star?
Well, it may give you a smaller star, yes. It will not give you a very, very massive star. So that's a good point. So the simple Eddington limit argument suggests that there is a maximum upper limit to how big a star can be. But there's a lot of detailed physics that we have to understand in order to figure out exactly what this limit is. For example, cooling of the gas as it collapses to form a star is actually very important. Cooling is accomplished mostly by dust and molecules which absorb thermal motion and re-radiate at very long wavelengths which escape the star. So you have a net effect of reducing the thermal pressure, turning it into long wavelength radiation that then goes out into space. And yet, we also have to bear in mind that stars can also be built up by other mechanisms. So you can have two stars that form by accretion. They may have fairly low mass. They may be in a binary system, for example, orbiting around each other. And they can eventually merge. And if they merge, some of the mass will probably be lost to the system, but the remaining object, the merged object, will maybe have a good fraction of the sum of the masses. So people have thought about the idea of how to build up large stars through this merger process. So the question is, what do we really know about the real mass limit? And to answer this question, we need to turn to observations. I hope that's what I turn to on this next slide. And I did. So to understand, I want to give you a sense of how we can determine the masses of stars in space. It's not an obvious thing that we can actually answer this question. And this is important to understand because it's also important to understand the uncertainties that are inherent in all these processes I'm going to talk about right now. So the best way to do it is directly by measuring the gravitational pull of one star on another one. And you can do this if the two stars are orbiting around each other in a binary system. You can measure the motions of the stars, the stellar velocities, and you can use that information to determine the masses of the stars, because that basically tells you what the force of attraction, the force of gravity is for each star. There's a couple of problems with this. Of course, not all stars are in binary, although a surprisingly large proportion of stars are actually in binary systems. They also, to use this technique, the stars have to be oriented in a special way. You really want the stars to orbit the stellar orbital plane to be along your line of sight, so that if the orbital plane is perpendicular to your line of sight, the stars, you can't detect the stellar motion. Also, you need to have the orbital periods be fairly short. Because if the stars have long orbital periods, what happens is it's very difficult to understand if the stellar motions are very slow, first of all, and it's very difficult to detect. You know, it's very hard to get astronomers to come back and look at the same star year after year. It has a 10-year orbital period to actually find out what the period of the star is and whether it's a binary or not. So that's a difficulty, but this is the most direct way we have of measuring the masses of stars. It's the exact same technique that we use to measure the mass of the sun by looking at the motion of the Earth. So methods 2 and 3 are more indirect, and these require understanding the detailed physics of how stars generate their radiation. So one way is to take the star's spectrum, take the light from the star, disperse it with a prism or grating, and look at the function, look at how the light varies as a function of its wavelength. And by doing that and some detailed analysis, you can get an estimate of what the star's mass is. As long as you understand all the physics, which is never actually quite clear, and we'll see in terms of very massive stars.
How do you get the mass from the spectrum?
Well, you can look at all the spectra have features in them,
Yes.
like absorption, they're called absorption lines or sometimes emission lines. The absorption lines are sensitive to the gravitational, the surface gravity of the star. So by using different models with different surface gravities and different radii, that can effectively give you the mass. We'll see in the case of massive stars that technique is very difficult to use because you can't see down to the surface of a massive star, so it makes it more difficult for extremely massive stars. Another way is to determine the star's brightness and temperature and plot it on a graph, a Hertzsprung-Russell diagram, and use observational calibration that tells you how massive a star with a given temperature and brightness should be.
It's an absolute brightness as opposed to some
That's right.
evident brightness.
That's right. So you really need to know the distance to the star, or you need to have the star in a cluster of stars, or the star could be in another galaxy whose distance you know through its redshift.
The word brightness is used kind of differently in optical physics and in astronomy.
Yeah, and I have to confess, I sometimes say brightness, I mean luminosity, and vice
There
versa.
you go.
So if I do that, I beg your indulgence. So anyway, with these three techniques, and there are more, but these are the three main ones. Number one is the best because it's a real direct measure of the star's mass. Number 2 and 3 are used most often because, as I say, not all stars are in binaries, and it's usually takes a lot of observational work to tease out the masses using radial velocity measurement. So those techniques work in general, but for very massive stars, let's say, I should define what I mean by a very massive star. A star with a mass of at least 10 times as massive as the Sun. And for the stars we're going to talk about tonight, we're really talking about things that are more like 50 solar masses or even greater. Observing these objects creates a number of challenges. First of all, these objects are very rare. So it's hard to find enough of these objects to do a large study. So if only a certain fraction of massive stars are in binary systems, for example, and only a very, very small fraction of all stars are massive stars, it's again going to be very hard to get a general rule of the run of mass versus stellar temperature, for example, looking at massive stars. A big problem is that these stars are so bright, they're really almost above the Eddington limit. And if you look at certain regions of light, certain wavelengths of light, at certain wavelengths the stars are actually above the Eddington limit. The stars are so bright that the atmospheres absorb mostly UV radiation, which has a big kick outward. And so the photons are streaming outward, hit atoms. The atoms absorb those photons, absorb that momentum, and get dragged along and get pushed outwards in the form of a very strong stellar wind. These winds are much more powerful than our solar wind. They're about a few 100,000 times more dense, for example. They have a velocity of, we talk about the hurricane, Irma's velocity of 180 miles an hour. These stars have winds have velocities of like 2 million miles an hour. So they're very, very powerful things. They take a lot. They transport a lot of mass at a very high velocity, and they can be very thick. They can be very dense. And so, in the very most massive of these stars, you can't even see down to the stellar surface. All you can see is the wind. And so since it's difficult to directly determine masses from massive binaries, it's actually also difficult to calibrate the indirect theoretical models that you need to, if you do a spectral or HR diagram type of analysis to determine the mass. So those are some of the issues and the problems. So now I want to talk about three and another three objects, really 6 objects altogether. Some of the case studies I think are very interesting. So the star HD 979550A1A, which I'm sure you all know, right? It's located in the Carina spiral arm in a cluster called NGC 3603. This is right now. This is a record holder for the most massive star that's ever been directly weighed. So this is an image of NGC 3603. It's this cluster of stars. There's, I think, about 1,000 stars here. You can see there's some very bright ones. You can also see this is a young cluster. It's still blowing away the cocoon of gas and the cloud of gas and dust that the stars formed out of. And this arrow is not really pointing directly at NGC 97950A1A. Let's just call it A1A, which is right at the center here. I think we have a better view of it. So this is a zoom in of that central region using Hubble, and now the arrow is pointing at this dot here that is composed actually not of one, not of two, but actually 3 stars in a single point of light, one of which is a star A1A, which is a binary, so that's actually 2 stars, so there's 4 stars in this single dot. A1A is has features in it that seem to originate from both components in the star. An analysis of these features as they move periodically has a period of about 3.8 days. As these features move periodically, and I'll show you what these features are in a minute, but as they move periodically, the analysis of their motion shows that A1A itself has a mass of about 116 solar masses, 116 times more massive than the Sun. An astounding value. Its companion is the lower mass, but still a monster star. It's still 89 solar masses. But you have to remember that when you look at a star, a very massive star, these stars are losing mass through this stellar wind and maybe through other mechanisms as well. But if you just think about the stellar wind carries off about 1 solar mass every 100,000 years. 100,000 years seems like a long time to us, but to a star, it's a snap of the fingers. So if you sort of extrapolate back these numbers backwards, to imagine what the star must have been like when it first formed, it implies that the A1A probably had a initial mass of something like 170 times the mass of the Sun. So somehow nature is able to put together enough material to make stars of 170 solar mass in our present day universe. But I want to sort of take a look at this in a little bit more detail, because I think this will give you an idea of some of the uncertainties of these numbers I just quoted. So here's A1A. So one basic problem is that of crowding. It's very difficult to resolve the individual stars. You don't really resolve even the individual binary system, even using the most powerful telescopes. So that's one issue. So you know, when you make an observation, you're going to have some background that you have to deal with. Also, the fact that these stars lose mass and you can't see down to their stellar surface means that you're dealing with messy regions like this. So here, what you're seeing here is a section of the spectrum of A1A, and actually this is A1A plus A1B, and you see there's this big, nasty looking thing here, these two narrow spikes, both here and here, and you can see that these narrow spikes are separate. These are actually, one originates from A1A and one from A1B. And so you can actually watch these narrow spikes move backwards and forwards with the Doppler motion of the two stars as the stars revolve in their orbits. But anyway, you're dealing with these features that arise from the winds of the stars, not from the stellar surface. And the winds, you know, are constantly blowing, they're constantly changing. So changes, variations in the wind can play an important role. Down here is what we call the radial velocity curve of the star. Basically, an estimate of, based on these features, of how the stellar radial velocities vary as the stars revolve in their orbit. When the two stars are moving either directly forward or directly away from you, the velocities are maximum. When they're moving across your line of sight, the velocities are lower, or minimum, are zero basically. And so what you expect is that the motion of the star will trace out a curve that looks something like the sine curve plotted here. And you see these dark spots are the data points from A1A's features, and they do agree fairly well. A1B, however, is a more difficult star to study, and you expect it to follow this dotted curve, and you can see that the points from A1B don't really agree with that curve very well. These are the best fits that can be obtained, but nevertheless, there's still a lot of uncertainty in these data. So even though, so this gives you some idea, you know, hopefully gives you some indication of like some of the uncertainties in studying these stars and deriving masses from this sort of the easiest way we have to do that.
Is A1C too small to have an effect?
It's I think it's it's either a foreground or background object. It doesn't really participate in the orbital motion at all. So now I want to turn to a star that, as John said, is sort of dear to my heart, Eta Carinae. This is I'll give you a sort of brief rundown of its history. At one point it was called Eta Argus. The Carina Nebula was originally part of the Argo, the Argus Nebula, which was named for the Argo, Jason and the Argonauts. Carina was great, carved out of that. Anyway, it's the most luminous star, as John already said, within about 10,000 light years of Earth. It may be the most luminous star in the Milky Way. I personally believe it is. Most people don't. But the other contenders are so much further away, so it's much more difficult to study them. We really have a very good handle on Eta Car's luminosity, and because we know its distance, and because it's so near to us. So I think this luminosity of Eta Car is much better determined than these other stars. So if it's the most luminous, it also should be the most massive star, just based on the Eddington limit. And the star itself is violently unstable. and sometimes it's called the Supernova Imposter, because at least one of these giant eruptions that it experienced back in the middle of the 19th century was at an energy of about it's about a tenth of about 1% of the energy of a standard supernova. So what I show you down here is time and brightness. So brightness is going up, and this is brightness now, and time going in this direction. So you see around 1840, the star went from rather second magnitude up to about -1. I show you here in blue and red the two brightest stars in our current sky, Sirius and Canopus. Canopus is Alpha Carinae. So you see Eta Carinae was brighter than Alpha Carinae. And this caused John Herschel, when he went outside to look, to be astounded. He knew Eta Car was fairly bright, but suddenly it was brighter than Canopus. And almost got as bright as Sirius. But then it did a strange thing. It faded away. And then it did an even stranger thing in 1890. It bounced up again briefly, and then it faded away again. And people sort of lost interest for a period of time till the 1940s and 50s. Then they started to look at the star again. What do you know? It started to brighten. And since then, people have been looking at it. And up to the present day, the star has done something like this. The star is actually getting brighter now, more than it's been in about 200 years. Yep.
Yeah, then is Eta Carinae a variable star?
Yeah, it's a variable star. It's one of the most variable
It's
stars.
a Peri, isn't it?
Well, I'm going to get to that.
Oh.
How do you know its distance?
Well, we know its distance actually in a number of ways. We can measure the cluster of stars around it, get distance from the cluster. We can also measure the motion of material that's expanding away, and that gives us a very accurate distance of the star.
Which is,
It's about 10,000 light years.
okay,
Yeah.
within.
Yeah. It's it's about, I guess, about 8,000 light years.
Oh, okay.
So the interesting thing about that is that the star is so massive and it lives for such a long time. The star might have already exploded. It may not be there any longer. We'll find out about it in a few thousand years or so. So I want to point out, I love this quote from Herschel. I love his title on the increase of magnitude in Eta Argus. Of course, he really means the decrease of magnitude, but I'm not going to quibble with John Herschel. He reported this in a famous paper to the Royal Academy. I have just observed a very remarkable phenomenon. And he goes on to talk about the changes in brightness that he sees in Eta Car. So, in the 1990s, there was a real change in our understanding of the star. Augusto Daminelli, who worked in Brazil, discovered what seemed to be a very regular period of about 5.5 years. And at the same time, we were looking at the X-ray emission from Eta Car, just so happened. And we also found that the star seemed to vary in X-rays. And so we started studying the star. So here in 1995, we turned on our detectors. This was on using an instrument called the Rossi X-ray Timing Explorer from Goddard. And we started studying the star. So here's the X-ray flux or brightness. And you can see it. When we first started looking at it, it wasn't really doing anything. We thought this was going to be a real waste. But then suddenly it started to increase and vary all over the place, and then it dropped very suddenly. And then it came back and did the same thing 5.5 years later, and then it did the same thing 5.5 years later. And then even another 5.5 years later, it does more or less the same thing. They're not exactly the same. There's changes from cycle to cycle, but this decline and this fall to this minimum state occurs every 23 days. So this confirmed the period that this guy Augusto Daminelli discovered. But it also allowed us to understand what was going on, what was causing the period. And what causes this strange periodic behavior in X-rays is that the X-rays are not coming from Eta Car itself, but they're actually coming from the interaction of the wind of Eta Car, this thick wind, with the wind of a hidden companion star. So we can't see the companion star, but we can see its wind in X-rays. And we can actually model this thanks to the X-ray observations and also observations with the Hubble Space Telescope, you can actually generate very sophisticated models in 3D that you can actually download and print. These are done by a colleague of mine named Tom Medora. If you have a 3D printer, you can get these off the web and print them. But what you see here are 3D models of the wind-wind interaction at various orbital phases. These are when the two stars are very far apart at apastron, and the interaction is sort of a shield-like structure. The wind of the companion star carves out a cavity in the wind of Eta Car. But the orbit's very eccentric, so when the two stars start to approach, the speeds of the two stars vary greatly. And this has the effect of making the wind-wind interaction zone sort of wrap in on itself and create a spiral structure. So you see here when the two stars are very close to Peri here and here, this wind-wind structure forms this nice Archimedean spiral. And we can actually see what we think is the remnants of this spiral expanding outwards from the star using the Hubble Space Telescope. And so this is a beautiful 3D representation to give you an idea of how unstable this interaction is. Let me go up here. Eta Car is this object here. This is the wind of Eta Car. The companion you don't see, but it's somewhere here. And the interacting winds form this cavity that spirals outwards and expands out into space. So it creates this spiral shell structure, which we can have now directly imaged from the ground using a very high resolution, high spatial resolution techniques. But this, the important point here in terms of understanding the star and how it's a binary is that we have a number of other objects that are much simpler to understand. A number of other examples of these colliding wind systems. And they all generate, or most of them generate X-ray emission. And so we understand how X-rays are generated in these wind-wind collisions. So the fact that we have periodic X-ray emission from this system allows us to model it as a wind-wind colliding wind system. So we think that so today we know that the star consists of Eta Car A, a very massive, very violently unstable star, and some other star called Eta Car B, which we don't really see directly, but again we do see the effects of the wind from the star. And that can be used to tell us something about the star itself. So the mass of Eta Car is very uncertain, even though it's a binary system. There is hope that someday we'll have observations where we can actually determine the radial velocity variations of the stars, of both stars, and determine the mass directly. That will be a very nice thing. We can't do that now. The best we can do is look at the spectrum of Eta Car and try to deduce what its mass is. Yep.
Will the Webb help with some of these observations?
Well, actually, the Webb can't, not for Eta Car, because Eta Car is too bright for Webb. It would burn a hole in the detector. In fact, Eta Car, I meant to mention this, it's an interesting factoid. Eta Car gives more heat to the Earth than anything besides the Sun and Jupiter, even though it's 8,000 light years away. That gives you an idea of how bright it is. So anyway, we don't really know what the mass is, but our current best estimate is about 90 solar masses. This is difficult to really constrain because of the thick stellar wind, and there's also a nebula in front of the star, so I'll talk about that in a moment. And the companion star, we really have no idea. I think it's about 30 solar masses. That would probably be about right, given the population of stars in the Carina Nebula. And a 30 solar mass star would have a fast enough and dense enough wind that it would be able to explain the X-ray emission. I should point out, the X-ray emission we see is all the X-ray emission generated by the wind of the companion star. The wind of Eta Car moves so slowly that it doesn't generate any observable X-ray emission. I don't really talk about the sizes of these stars, but just to give you an indication for Eta Car, if you put Eta Car where the sun is, it would swallow Venus. That's how big it is. It's about the size of the orbit of Venus. And also, because it has this thick stellar wind, the wind is actually more opaque at certain wavelengths than others. So at certain wavelengths, the thickness of the wind is so thick that it would block all the planets from being viewed out to about the orbit of Uranus at that particular wavelength. So the question is, how much mass did Eta Car have when it first turned on its nuclear fires? This, of course, also is very uncertain. And it's important to note that the masses of these stars decrease because of the wind, but also perhaps because of large eruptions. So these stars can be very unstable. At least this one particular example, Eta Carinae, is extremely unstable. We know of other similar stars, but that are similarly unstable, but not to the same extent. Eta Car had this large eruption, and well, here you can't really, didn't really come very well. Eta Car has a very famous nebula around it, the bipolar nebula. You can't really see that. Surrounding the star itself is this white dot here. This homunculus, this nebula is called the homunculus because it looked like a little person in early ground-based observations. This homunculus nebula was formed sometime during this great eruption. And in fact, if you look down here, what you're seeing is these arrows represent the motion of different bits of this nebula as it expands outwards. And you can see the arrows are all pointing away from Eta Car. The material is all expanding outwards. You can actually, there's a nice movie in which you can actually see the expansion in quasi-real time, taken with Hubble. And if you extrapolate these arrows backwards to where they originate, you find they originate with Eta Car. And given the apparent velocities, you can deduce, assuming that the flow is uniform, you can deduce that they all originated in around the 1840s. So if you look here at the scale here, the colors of these arrows represent when the material was ejected. So all this material in red here was in the 1800s. There seems to be some material out here that might have actually been ejected in the 1200s. Either this is material that was ejected long ago, or it's material that was faster, moving material ejected in the 1840s that perhaps got slowed down somehow.
Could you move to your left a little?
Is that on my left or? Yeah, move back over here. So the homunculus nebula is very interesting, not only because it's a beautiful example of a circumstellar shell, but it's also important because we can measure the mass of the homunculus nebula by looking at how much dust it contains. And from the dust, we determined that the total mass, dust plus gas, of the homunculus nebula is about 20 or 30 solar masses. So this material, you can imagine 20 times the mass of the sun being ejected out into space in the period of maybe a year or so, maybe 10 years. We're not exactly sure. There's some discrepancy for all these times, some uncertainty for all these times, I should say. But this is an enormous amount of the mass of the star. It's something like removing the outer 1/3 of the star, so the star is only 2/3 the size it was before. Why this happened is still one of the outstanding stellar astrophysical mysteries of our time, and it's been a mystery since it happened back in the 1840s. So it really is an extraordinary phenomenon that, as John Herschel noted. So not only can you have mass lost due to stellar winds, but you can have mass lost in these giant eruptions. And we have almost no understanding of how frequently these giant eruptions occur, whether this eruption was unique to Eta Car, this event was unique to Eta Car, do other stars also undergo it, go through it, what causes it, what triggers it, no one's really sure at the moment. Models of this eruption include stellar mergers, so people say, well, this happened because a third star got swallowed up by Eta Car A. If that's the case, though, that doesn't really explain why you had this material, this older material, if this material really is older. There's other strange models as well, having to do with how the star generates nuclear reactions at its core and how unstable that could be. But anyway, we're still watching it, and hopefully, at some point it'll explode during our lifetime, and we'll be able to stop watching it, but also tell a lot about the star itself. Okay, so I want to move on now beyond the Milky Way. So Eta Car and A1A, the previous star, were all within our galaxy. R136A is perhaps the most massive star in the Large Magellanic Cloud. The LMC, of course, is the neighboring galaxy that orbits around the Milky Way. It's about 200,000 light years from the center of the galaxy. The LMC has this famous cluster called the Tarantula Nebula, a famous nebula called Tarantula Nebula, embedded within which is a cluster called R136. And this background image is actually the R136 cluster and the Tarantula Nebula. This Tarantula Nebula is home to enormously bright stars, so it's similar to the Carina Nebula in our galaxy, but it's actually much has much more massive stars. At one time, this star at the center here was thought to have a mass of 1,000 solar masses. So that was an astounding thing. It was shown that that's not actually the case, because if you look at that single object, and we'll do that now, you can see that this single object, which is here, is actually resolved into a number of stars, A1 and A2. And so here's this square, that's that square, and inside this cluster are these stars here, A, B, and C are these two stars here. So this is my favorite paper title of all time. The R136 star cluster hosts several stars whose individual masses greatly exceed the accepted 150 solar stellar mass limit. This title is almost as long as the number of letters to object. But it's very exciting. You can understand, this was a colleague of mine, Paul Crowther, who wrote this paper. You can understand the excitement of this discovery. And he didn't want to bury it in the paper or bury it even in the abstract. He wanted it to be the title. It's a very straightforward title. So Paul and his team looked at these stars in the Tarantula in R136 and the Tarantula Nebula, and made analyses of their spectra and also their brightness, and compared where their brightness and temperature fit with evolutionary models, with estimates of their ages, and came to the conclusion that the initial masses of these stars, of many of these stars, and particularly A1 here, ranged up to 300 solar masses, and they claim that A1 is a 300 solar mass object, initially. So this is not the current mass, but the initial mass, or at least their estimate of the initial mass. And at the time, there was a famous paper claiming that based on studies of stars in the center of our galaxy, that there's a mass limit of 150 solar masses. So Crowley was excited because it seemed like nature had a way of making stars up to 300 solar masses. Of course, both the center of the galaxy and the LMC are very, very far away. Particularly, the center of the galaxy is even harder to observe because there's a lot of gas and dust between us and the galactic center. So both these observations, I would argue, and Feiger and Crowther will probably disagree with me, but I would argue that these observations are prone to intrinsic biases. So I think there's some uncertainty here. In particular, we've already talked about how the central object was thought to be a single object at one point, and we now know it's been resolved into multiple objects. It may be that A1 itself is resolved into multiple objects at some point in the future. Yeah.
Would this limit of 150 solar masses depend upon the metallicity of the material?
Ah, yes. So everything I've been talking about is in the local universe. And this implies that all these stars have metallicities that are close to, similar to the sun. In fact, for the LMC, the metallicity of the LMC is much lower than the metallicity of the sun. So the idea that these objects have these masses is dependent upon the metallicity, and it's also trying to extrapolate back to the initial mass of the star. You have to understand how much mass the star is losing through its wind. And when the star loses mass through its wind, that depends on the metallicity, because if the star has a lot of complex chemicals, those chemicals can absorb more radiation than a star that just is composed of hydrogen and helium. We'll actually come to this in a minute when we talk about stars in the very early universe, where there are no metals. So finally, I want to leave our test cases or examples with three exciting objects, or actually three exciting events. Gravitational wave detections. One that happened in 2015 September, 2015 January, and then 2015 December, and 2017 in January. These events may be fossils of giant stellar beasts. So you've probably seen the announcement of these gravitational wave events are extremely, we're really fortunate to be living in this time. This is almost like we're living at the time of when Galileo took a telescope and pointed at the heavens, or when Newton showed that you can disperse light into a spectrum, and people started to look at the multi-wavelength universe. This is the first time we're actually opened an entirely new window on the universe by detecting gravitational radiation. And the first time we were able to do this, or I should say the LIGO team was able to do this, they found something that people suspected but never saw before. LIGO, as you probably all know, is a dual kilometer scale gravitational wave observatory. There's one located in Livingston, Louisiana, and a companion in Hanford, Washington. They have 3-kilometer beam lines, one that goes in that direction, one that goes in this direction. They send a laser beam down each beam line, and it bounces back, it gets combined over here. And by doing that, they're able to measure very, very precise changes in distances. Changes in distances are so small, they're actually smaller than the size of the radius of a proton. LIGO has so far detected 3 events. There's a 4th one that's not really very high significance, so maybe a 4th one. But there is actually a recent event that's been rumored in all the astronomical websites and blogs that you can easily find. And it's very interesting. Object, well, not having to do with what we're talking about tonight. So you can't see this too well, but you can hopefully see this. So what you're seeing here is a measure of the change, effectively a change in the distance between the ends of these beam lines, as measured by these laser beams. And what you see is that the beam lines are the distances are pretty constant, and then all of a sudden the distances start to oscillate. It oscillates very rapidly, and then it hits like a crescendo and then stops. They see this both in the Hanford data up here and the data from Livingston, Louisiana down here. And if you look at the data, this is overplotting both data sets. You can see they both basically tell the same story. And unfortunately you can't really see this. But what these variations, these oscillations are due to are the passing of a gravitational wave. A gravitational wave that's changing in amplitude and frequency. A wave that's generated by a very unique event. Well, maybe not so unique. Unique in the sense that we've never seen it before, but maybe not so unique. The event was the merger of a black hole binary. So you have 2 black holes, if you can imagine that, just like you have 2 stars, they spiral around each other. By Einstein's theory of general relativity, as a spiral or as they orbit around each other, they generate gravitational radiation. And that emission of gravitational radiation causes the orbit to decrease because it's basically a loss of energy from the system. So the stars start out fairly wide apart, and then they sort of spiral together. When they spiral together, at the very last stages, they spiral together so rapidly they generate these very rapid oscillations that increase in frequency until they finally merge. And there's sort of a ring-down effect in space-time. And that's what you see there. So these variations, you can actually model them using general relativity. And that's what the LIGO team did. And they were able to deduce what caused these oscillations, this waveform. And they said it was 2 black holes that merged together, one of which had a mass of something like 35 solar masses. The other one had a mass of something like 27 solar masses. And they combined together to form a a black hole of about 60 solar masses. You don't read that long. Yeah, about 35 and 30. So the combined mass, the final mass of the black hole that was left behind is actually less than the combined masses of the two black holes, and that's because of the energy that's carried away through the gravitational radiation. So LIGO has shown that there's a population of black holes having masses of 5 to 35 solar masses. This is very unusual. We had no idea if such a population ever existed. And people are working very hard to understand how black holes of this mass can come together. One way in which they could be produced is through the evolution of stars that are something like 100 or a few hundred solar masses. Of course, you can build them up by combining smaller mass black holes as well. So there's a lot of uncertainty here. But there at least one channel that you can produce a 30 solar mass black hole would involve a very, very extremely massive star. So I should run through the sudden death of stars. The thermonuclear sequence for stars, very massive stars, cooks up things from carbon all the way up to iron. When iron forms in the star, that's a bad thing because iron has no, you can't extract any energy from iron. And once the iron core forms at the center of a star, the star will collapse in on itself and cause a supernova. For very massive stars, that's sort of a weird thing because the core is so massive that it will collapse directly to a black hole. And the black hole will start to eat the star that it's embedded in. And this produces a jet, like this, that actually blows the star apart. So at the very center of the star is a black hole that formed, material spiraling into the black hole. A jet is produced off the accretion disk, and that jet produces a burst of gamma rays that we would see as a gamma ray burst here on Earth. And finally it leaves behind this black hole that will slowly accrete the remnants of the disk, that's all that's left from the star, and form a 10 solar mass, 5 solar mass black hole or something like that. But black holes don't only end their lives like massive stars don't only end their lives like that. They can also end their lives through something called Peri instability supernova. And this happens when the conditions at the center of the star, for very, very massive stars, more than 130 solar masses or so, conditions at the center of the stars are so hot and so dense that radiation that's generated at the center has such a high energy it can spontaneously discombobulate into matter. So the gamma ray radiation that's generated in the core of the star can actually form an electron-positron pair. And this has an effect of reducing the thermal pressure of the star itself. And as that thermal pressure is reduced, the star will rapidly collapse. That collapse doesn't form a black hole, though, because what happens is before the black hole can form, the collapse heats up the overlying layers that are still pumping out thermonuclear energy and drives the reactions to a runaway state. And the runaway reaction will be powerful enough to blow the star apart altogether. And that can result in the complete destruction of the star without leaving behind a black hole. Another interesting thing is that the star can just collapse in on itself and disappear. And we think we see an example of this. So if the star is massive enough, the black hole that will form when the core collapses can be massive enough that the material will just fall into the black hole and the star will effectively disappear. So here's a star in an external galaxy, NGC 6946, seen with WIFPIC in 2007. And if you look at the same field back in 2015, it appears as if the star has just disappeared. No one has seen an explosion from this star. If you look very closely here, there may be a hint of something left behind, but there doesn't appear to be anything very strong left behind. So this is the one and only case where we think we may have seen a star directly collapse on itself. So stars not only explode in brilliant flashes of light, perhaps they also, some just wink out of existence. So I want to finally finish up by just a brief discussion of massive stars through time, so I'm not going to talk about the entirety of that time, but I want to think about stars that formed right after the Big Bang. You know, when the universe was first formed, the universe only existed in the form of hydrogen and helium. Those are basically the only two elements left together. Of course, you can have hydrogen in atomic and molecular form, helium just in atomic form. There's probably some deuterium and tritium and so forth. So out of these simple elements, you had to cook up stars. So without cooking up stars, the universe would not evolve at all. The universe would not produce small stars, and would not produce planets, and would not produce people. We talked about cooling the gas, contracting gas cloud. And in the modern universe, in this chemically polluted universe we live in, the cooling is done by dust formation and molecules. But back in right after the Big Bang, there was no dust, there weren't many molecules. So it was very, very hard to cool a contracting gas cloud. Which means that only the most massive gas clouds could contract to form stars. That means that the first stars that formed in the universe, the first generation of stars, had to be extremely massive. So while we know today in our local universe massive stars are extremely rare, in the early universe massive stars were common. And these stars formed about 100 to 200 million years after the Big Bang. They produced the first light in the universe. They produced the first complex chemicals by running through the thermonuclear processing: carbon, nitrogen, oxygen, neon, silicon, iron. And some of them dispersed them by exploding. Some of them probably just kept them to themselves by swallowing them up as a collapsed star and just forming a black hole. Early massive binaries probably produced the first carbon-rich dust in their colliding winds. We see this process happen in the current universe. Must have happened back in the early universe as well, if the wind had enough carbon in it. And the molecules and dust produced by these first generation of stars allowed stars like the Sun to form and allowed planets to form.
Why does a carbon particularly formed in double stars?
It's not particularly formed in double stars, but a single very massive star will go through the triple alpha process, where you have 3 helium form a carbon atom. And that carbon gets dredged up by instabilities in the envelope of the star. So it gets transported from the interior of the star by the core through the envelope to the surface of the star. And once it's at the surface of the star, it can help draw the stellar wind.
But you say early binaries.
Right.
Both.
So if you have a binary system, what happens is the carbon-rich wind smacks into the wind of the companion star, and that interaction will compress the carbon in the wind to form molecules and to form dust. And in fact, we see this happening in systems like WR-140 and some other systems, where when the stars get close together, compression takes over, and you see a large amount of carbon-rich dust forming.
If the gas can't cool, because there's no heavy elements, wouldn't that lower the Eddington Limit and force smaller rather than more massive?
Well, it's actually the reverse, because what happens is, even if you had like a 10 solar mass cloud trying to form a 1 solar mass star, the temperature in that 1 solar mass collapsing core would be so high and wouldn't be able to cool efficiently that it would not be able to really form. So you really need a lot of mass pouring in on that core to...
Doesn't the higher mass pouring in mean you're heating up more? Because at the beginning you said that the radiation produced goes faster than the gravity effect of increasing the mass.
It can. It depends on the details. And if you get very, very high mass, very low metallicity, you can actually gravitationally collapse a very, very large mass, even though it has a large internal pressure, as long as that mass is going to be greater than the internal pressure. So that's really about it. That's sort of the story of the extremely massive stars. I think they're really fascinating objects and produce a lot of very interesting events and phenomena. So I just want to leave you with a couple of thoughts. So although we have a good understanding of the physics of star formation for lower mass stars, there are a lot of uncertainties in our understanding how extremely massive stars form. And measures that are direct and indirect of stellar masses suggest that most stars can have the most massive star can have is around 300 times the mass of the Sun. But of course there are significant challenges in deriving these stellar masses observationally. I hope I've convinced you of that, and also theoretically. In the early universe, we think that the most stars were extremely massive, and these stars helped shape the early and subsequently the modern universe. And I just want to finally end with a plug for the James Webb Space Telescope, which may detect the first light from these first generation of stars. And this is the James Webb Space Telescope at the clean room of Goddard. Here's the mirror. You can see it pointing up at the ceiling. This is James Webb at the vacuum in the clean room at the Johnson Space Flight Center. Johnson Space Center, rather. This was taken a few days, I think, before, maybe a couple of weeks before Harvey landed. So while they were actually testing JWST in this large vacuum chamber here, as Harvey was raining down on Houston, evidently Johnson survived okay. They had, I think, a one-day delay that they were able to make up, so things seemed to go okay. Launch will be about a year from now. It'll last about 5 to 10 years. And it's got a primary mirror diameter of about 6 meters, and its orbit is going to be at the so-called L2 point, which is sort of on the opposite side of the Earth from the Sun, along the Earth-Sun line, and it's about 1.5 million kilometers from Earth. So unlike the Hubble Space Telescope, JWST will not be serviceable, so if anything goes wrong with it, it's sort of out of luck. It's going to be a very exciting time for astronomy. And this is a film by our good friends at Northrop Grumman on the launch of JWST. So I will just let this play, and if you want to turn the lights up, and if there are any other questions, I'll just end it there.
I have a question.
Yeah.
What in the spectrum, in the scale thing, how big is Betelgeuse compared to the massive stars that you're talking about?
Betelgeuse is a real giant. So some of these lower mass stars, red supergiants, become really large. I want to say it's about the size of it's bigger than the size of our solar system. I can't recall the exact number right now.
Okay. But it's okay.
Yeah.
They're very dense, they're very massive stars. If I understand, there's a search from Russell arc.
Right.
I forget temperature and I forget what.
And brightness.
Right. But some of those don't follow the main sequence. What's the difference?
Well, when stars form, they do fall on this main sequence band. It just has a little spread to it. The thing with very massive stars is they don't spend a lot of time on that band because they evolve so quickly.
Also, they all do follow that arc.
Yeah.
Oh, I see.
Yeah.
You hinted that Eta Carinae has a short life.
Mm-hmm.
Would you care to prognosticate out?
Well, it's hard to determine exactly when it's going to blow up because there's a lot of debate about what's going on in the core. We think it may be burning helium in the core based on some analyses of the spectra. If that's the case, and the abundances that you see, if that's the case, then the helium stage only lasts for about 100,000 years. And it would just blow up after that.
We don't know where we are in that.
No. And if it's still burning hydrogen, it could be millions of years. And if it's past helium, then it's really short.
If it's on the L, if the Webb is going to be the L2, won't the sun be between us and it, and how are they going to be able to communicate with it?
No, so here's the sun, here's the Earth, here's James Webb. And it follows the Earth in its orbit, so it's always on the sun's always on this side of it.
Okay.
In fact, Webb operates in the infrared, so it measures heat. So it has to be kept extremely cold, so it can't have any sunlight fall on it. So it's got this big, I don't know if it's deployed, there goes deploying, can't really see this unfortunately. But it's got this big tennis court sunshade, it's actually like 5 layers thick, that is designed to keep the sun off it, and designed to, that micrometeorite don't penetrate it, and allow sunlight to fall on the instruments.
When Eta Carinae does eventually explode, will that be of any danger to the Earth?
Well, that's actually something that people have looked at. We don't think it will. If it is one of these jet-driven supernova, presumably if we were in the jet, we would have some. There would be some danger to us. It could destroy our ozone layer, for example. We think that the jet would be directed along the rotational axis, which we think is aligned with the axis of the homunculus. And we know what that is very precisely. So that's not directed towards, so here we are, the homunculus axis is about like this. So we think the jet would squirt out sort of perpendicular to our line of sight almost. But the other thing is, rotating objects change their axis of rotation, so I don't really know what the current axis of rotation is.
And how long would it take for this to get to us?
Well, it would take 8,000 years.
Yeah,
If it
exactly.
exploded 8,000 years ago, it could be tonight.
Yeah, that's right.
Stars, when they die, can either form white dwarfs, neutron stars, or black holes. Or none of those.
Right.
But what are the approximate cutoffs? I think to get a white dwarf, it's a star up to about 8 solar masses. And what's the approximate cutoff between neutron stars and black holes? It's about 20, 25?
Right, so that's a question we don't really know, because we don't know what nuclear matter, for a neutron star, we don't really know what it's made out of. We don't know how the matter behaves at those extreme densities. So we're not really sure how much mass a neutron star can withstand. We think it's around 3 to 5 solar masses, maybe about 3 solar masses, I think is most, would be what people mostly agree on. There's actually an experiment on the space station right now that's designed to help us study what is inside a neutron star by looking at the length bending effects of the neutron star, of an X-ray pulsar. The cutoffs are all determined by the core mass, basically. So for a star like the Sun, the core mass, will be about half a solar mass or so. They'll form a white dwarf. Stars up to 8 solar masses probably will form neutron stars in their core, and then, up to probably around 10 solar masses will form neutron stars, and above that they'll probably form black holes.
I was wondering, does the Chandrasekhar limit come into effect? Yeah, there was something over 1.6
Right.
solar mass.
Right. So the Chandrasekhar limit's an interesting concept. It's really applying quantum mechanics to stellar structure. And so what you have is that once a star's energy resources are totally gone, the core is totally inert, there's still a pressure. And the pressure comes about because the electrons start to whiz around. And the star will collapse to a certain point until the electron speed, because of quantum mechanics, approaches the speed of light. And when that happens, that produces a quantum mechanical pressure that supports the star. But of course, the speed of light is an ultimate limit. So if you add more mass to this object, the electrons get squeezed enough, but they can't produce enough pressure because they can't go faster than the speed of light, so the object will collapse. And that limit is called the Chandrasekhar limit, as you say. And that's what holds up a white dwarf. Neutron stars have something similar, but the physics of neutron star material is much more complicated than it is for normal matter. We understand how electrons move in normal matter, but we don't really understand if electrons even exist in the interior of a neutron star. I mean, maybe free quarks, in which case no one understands how they behave.
Let's thank our speaker.